Um, Hi everyone, welcome to today's video, and today we'll learn about symbols, water symbols, and what do they mean in binary. And then we'll also try to look the difference between the availability of symbol in stripped as well as unstripped binaries. If you're still unsure about the stripped or unstripped binary, please go through our previous videos. We have a very good video on that topic. So for today's example, we'll go with this hello world program, which is nothing but a main function. You have a variable called var and you are printing the hello world. Then after that, you're printing just the variable. Right. Now let's talk about water symbol. So you have this high level source code, right? And you know there is a main function and there are variable inside it. So these are the high level functions. But when you generate a compiler using a compiler like GCC, now you have a binary. Let's say we do this hello world.c and then minus o and then hello world, right? So this is the compilation process. Once this is done, we can check with the file utility what kind of object is this, and you'll say it's an ELF object, 64-bit ELF object, and it's a binary basically. Now, when you go through this binary, so let me show you some examples. So object dump is the tool which basically disassemble a binary and give you the assembly level. If you do object dump minus D hello world and then just enter maybe, so you will see this is how a binary looks like. It has a lot of compiler introduced code, but if you go inside this specifically text section, this is where the code lies actually. And then if you go to the main function, this is the whole main function. So you can see a very difference between how a binary looks like. This is not even a binary, it's just one level up, that is assembly language. And now you have on the right is your main function. So see, um, there is technically a lot of difference, and to maintain this mapping of this var to this particular binary function, or the mapping of this main function to this particular binary function, you need this kind of informations, and these are called symbolic information. So there can be multiple type of symbolic information, like function wise symbolic information, within function variable level symbolic information. So there are a lot of kind of symbolic information, and we'll discuss one at a time. But now next, let's talk about why it's important. Why do you need symbol? So if you have an understanding of the four-phased compilation process, at the end, the linker. So if let's say your project has like 5C files, and from the 5C files after compilation, you have 5 object file. Now the job of the linker is to combine all of them in a binary file. So in that linking phase, these symbolic informations are used as references to combine all of these object files into one. And the second thing is debugging. We all know what breakpoint is. We have to put breakpoint in any ID or GDB, and then we try to debug in terms of source level code, right? So in there also, to map this mapping, so have the mapping between this source level variable or binary level, these informations are very important. So in short, if you are a reverse engineer, this information is the best information near to the source code you have. If you don't have it, your life can be very difficult. So, and to show this symbolic information, you can use this tool called readelf, and then you give this information input sims, then you provide the path of your hello world program. So this is how you can see all the symbolic entries, and this is basically the symbolic entries for our hello world program. If you see, it's largely divided into two things. Symbol table, this is called dynamic symbol table .dym, and this is the local symbol table you have. So why the dynamic symbol table is needed? So for example, you can see there is this puts function. So whenever you call printf function, it's by default call the puts function, or maybe GCC compiler use some other kind of puts function to print something on the terminal, right? So these are basically not part of your code. It's coming out of a dynamic stdio library, right? So that whenever you run this code on the runtime, this resolution of puts function has been done via this dynamic symbolic table, and then you run the code of the puts and print something in the terminal. So these are all the unresolved external symbols you have, which will be needed during your system processing, but it's right now not present in your code, right? You just call the printf function. um then you have this symbolic information, as you can see, like a lot of stuffs, right? But the majority, but you can see in our C code we all only have the main function, right? So the rest of the functions like this, then do global detour, then fini, these are compiler introduced functions. So compiler needs to introduce something to make the binary a full-fledged binary and run on its own. So those are not user defined. However, if we look at the main function, is this line 32, you can see, so first one is the offset. So starting from the binary after 1169 bytes, you have your main function, which is around 73 bytes of size, and it's of a function type, and you can say, right? So this is how the symbolic information uh, looks like in a non-strip binary. Oh yeah, so if you still go through your hello world, you can see, so this is non-strip, and by non-strip it means all the symbolic information is present, but explicitly you can strip the binaries out and strip all of the symbolic information. And why it's needed? So let's say you have a company, you are generating this binary, but you don't want other reverse engineers to easily find out your uh, code logic, right? So if you have this, it gets easier to understand how the code looks like. For example, if we again do objdump d minus hello world, you see there is a clear distinction between each function, but whenever you strip that, you don't have this clear distinction, as well as you don't have the symbol table. Let me show you with an example. So by stripping, all we have to do is call this strip function. Me clear this. All you have to do is call this strip function with this tag strip all, and then your hello world. Okay, so previously you saw it was showing that it was a non-strip program. Now it is showing it's a strip version. Now if you do the same thing and try to read the symbolic information of this stripped hello world, sorry, my bad, something is wrong. I think it's sims, not sim. So if you do this, now you can see there is no localized symbolic information. All you have this dynamic symbolic table, right? And why it's needed? Again, even with strip binaries, your binary doesn't contain the printf function, right? It has to be loaded dynamically in the operating system during the runtime. So that is why it still have all those undefined, unresolved symbols, basically, which the code is going to use later in its execution. So now this is symbolic information. I would also like to show you how the clear distinction between the main function will be missing in a strip binary. So for that, we'll use our object dump minus d and our strip binary. So you can see now this is, so again, this is the text section, and this is where all the code lies. And it's just now a monolithic piece of code, and there is no distinction of where the main function is. So obviously, if you know the source code, you can come out and, the code is same. Again, you can try to identify, okay, maybe somewhere from here, the code is starting and going till red or something like that. So it's still doable, but it just makes your life uh, way harder, right? So yeah, so that is why stripped is sometimes important for the company or for an individual to make reverse engineer, to make the life of a reverse engineer a bit hectic, or maybe to stop hacking, right? Once that's done, I would also like to talk about a few more things. So far we just saw a symbolic table where we could identify the main function. But what if I want to identify this variable, right? Again, on the symbolic information's only present in unstripped binary. So we'll just compile our hello world and sorry, my bad. There is minus O, and we'll make sure that our hello world is again non-strip, because otherwise we will not have any symbolic information, right? So one thing I showed you is that symbolic table information, but there is other kind of symbolic information, particularly for this ELF binaries. We have the dwarf information, which is already embedded in the binary file, but in a separate format. So it has its own formats and it has its own difficulties, but I'd just like to show you where this information of the where lies inside the main function. So to get the dwarf information, I am using this tool called LLVM dwarf term. If you just simply install LLVM, you'll have this. And then simply, if you want minus I, you can put minus Y. Otherwise, just simply hello world. It will it is saying, oh, it is saying there is no dwarf information. So there is a compiler flag. You have to explicitly give it gcc minus g3 hello world.c and then hello world. So it's not by default included in your binary. So you have to give this g3, and let's check whether it's still non-stripped or not. So it's not stripped. Now we'll again use our dwarf term tool with the hello world, and it will give us a lot of information. So I'll skip most of it because it's just not the correct time to describe, neither we have the scope. But the important things to just follow my highlighted portion. So this is a program type of information, and the name of the program is main. And we have argc and argv as formal parameters. So you can see we have one formal parameter, then another formal parameter, and here lies our where. And we know it's int type, so you can go to its type information and get the int type, etc. And you can also look at the file location, etc., etc. So yeah, in short, these are like two types of symbolic information. One is the symbolic table you got out of the binary. If you want this information, for ELF is dwarf, for p file, which is a Windows file, you have pdb, and you can extract the dwarf information. And if you want, you can further analyze to get any information out of it. But the major usage is again to link this high level source code and binary, right? Thank you all for listening to me, and maybe next time we'll discuss about more detailed about this disassembly and the object tempo. Thank you.